Hello and welcome to Chapter 9 of Statistics. Hey, we're going to talk about the sampling distribution and then building confidence intervals for proportions today. If you've not viewed the introductory video that talks about how to build a sampling distribution, you should pause this video or stop it and go back and do so now. All right. So today we're going to be talking about the sampling distribution. So what we want to do is we want to investigate what is the proportion of the population. So you might be interested in something like, I don't know, what proportion of your customers are first-time buyers? And you might have some inkling on what that group looks like, but usually it's too large for you to actually measure it. So what we want to imagine is, okay, clearly I can't get a population value here. So what I'm going to instead do is grab a sample and see what my sample looks like. But one sample probably isn't enough. So let's grab lots and lots and lots of samples. And then if we look at the collection of all samples and its distribution, then maybe I can figure out overall which samples are most common, and that would represent really what's going on in my population. So what we're going to do is we're going to imagine the possibility of what happens if I look at all the possible samples. One of the things we know is that because of sampling error, not all of my samples will look the same, which means one group of proportions that I'm out there looking at might be totally different from another group. So if you're having a hard time picturing this, imagine that you and I were both interested in figuring out what proportion of our customers were first-time buyers. So I go out and grab 10 customers and ask them, hey, was this your first time purchasing from us? You go out and grab 10 customers and ask, hey, how many of you are first-time buyers? And I might come back and be like, well, it's 3 out of 10, so I'm at 30%. And you might be like, oh man, I'm at 4 out of 10, so is it 40%? Which one of us is right? The answer is really both of you. You both were talking about samples, not populations. So the idea is if you look at all the possible samples, we get a distribution, and we'll have some better idea of how they all look when coalesced together. So I'm going to one of the ways you can do this is by looking at simulations, and that's in the introduction video. So if you haven't watched that, please do so now. So think about it like going through all of them. There you go. All right. So again, we'll probably never actually know the true proportion P, this guy, P. But instead, what we want to do is try to get the best guess we can for it possible. So remember, we'll never actually know P, but we can gather lots of samples and see what's going on. So as you're looking at this next histogram I'm going to show you on the next slide, it's me doing 10,000 samples of proportions, where I'd already set the true proportion to be a value in particular, 0.20, and I used a sample size of 1,000. So we grabbed 10 people in my sort of thinking about it example. Here, we're going to be doing 1,000. Sorry, yawny. Not every sample will have the proportion 0.20. So just like me grabbing 0.3 and you getting 0.4, there's going to be some variation here. And certain samples are going to be more common than others, like, ooh, stuff around 0.2, definitely more common than like around 1.6 or 0.24. And we notice that most of the sample proportions are between 0.18 and 0.20, with a few being not so off of that. We call this the sampling distribution. And the way we symbolize that is we say that this is actually the distribution of samples. So we think about it as being p hat, the variable p hat. So remember, p hat stands for sample proportion. So as you look at this, I'm looking at all the sample proportions. So this is the distribution of all samples. It's called the sampling distribution. Name makes sense. Good. Okay. Remember that proportions are based on two ideas. I look at a single event that has some defined success or failure. Going back to the verbal example I was giving you earlier, our success was, oh, you're a first-time buyer, you're a first-time customer. Our failure would be, you're not. Now, this isn't necessarily a success or a failure. It's just the success is the event you're interested in. The failure is the event you're not interested in counting. So when we look at the simulation, all of our p hats came out different because we were doing random draws of random samples, and then we looked at the proportion of successes in those samples. So even though p hat is going to vary from sample to sample, it's going to be in a way that we can actually model because it had a clear and defined shape. This is what we call the standard deviation of the sampling distribution, this guy. So it's talking about the spread of the sampling distribution. So SD, standard deviation, of, not multiply, the samples. So I'm looking at the spread of the samples, the spread of the sampling distribution. And it's not too surprising what this looks like. It's the number, it's your success times your failure divided by the square root of n. I talk a little bit about this in some of the other videos. But as you're looking at this, it's going to be different for every single sample size. So in here, I calculated what it would have been for my particular example that we just did. So the histogram I just gave you. So one thing to keep in mind as you're doing this is that sampling error is not really an error. It has one of the worst names in statistics. It's not so much an error as it is variability. It's the difference between selecting different samples. And sampling variability is normal. You should have some variation amongst your samples. If all your samples are the same, that would be super weird, and usually is a sign that your data is fabricated. So be careful. I mean, it is true that using a sample instead of the population to do these calculations isn't the best idea in the world and will cause some differences, but it doesn't mean that it's an error. Okay, so what does a sampling distribution look like? Well, when it's normal, it looks like the following. Its mean is the sample proportion. Its standard deviation is what we saw earlier. It's p times q divided by n and then square rooted. And this is what we call the sampling distribution model for the sample proportion. Another way you might see this written, just so you know, is that my sampling distribution is distributed, that's what that tilde means, by a normal distribution. Remember, the n stands for normal, with mean p, and standard deviation of the sampling distribution. And that's just the same thing as saying this guy up here. So don't let that fool you. It's just a matter of saying I'm using the standard deviation. And one thing to keep in mind as you do this is notice that our sample size is in the denominator, which means that as I draw larger and larger samples, my standard deviation gets narrower, so my distribution gets narrower. So what does this look like? Well, there's our center, and then we add and subtract standard deviations until we get there. This has a little bit of an error in it. It really should be p plus, p plus, p plus. This already has the minuses in it. It should be p's and p's and p's and p's and p's. It's just how far I've gone in each direction. So now that this is normal, I know what my spreads typically look like. I know that I'm moving, if I move one standard deviation in each direction, as in from here to here, that's 68%. If I move two standard deviations in each direction, that's 95% of all proportions. And if I move three standard deviations in each direction, that's 99.7% of all proportions. So you should be thinking of this as, oh, it's normal. I know what normal looks like. I know how to do normal calculations. What this does is it takes a complicated problem, what's the population proportion, and reduces it down to something we know. The price you pay, though, is that this is about a sample, not an individual. So how good is this model? How normal is it going to be? Well, if you're just using sample size of 1 or 2, it's probably not going to work very well, because it's not actually going to look very normal if you do that. The larger the sample, the more, for these histograms, the more normal it looks, and it actually becomes more normal if it's large enough. So you should be asking yourself, how large is large enough, lady? That's pretty vague. Let me go through exactly when that happens. So the first condition you need for this to actually work and actually be normal is you need the independence assumption. So this is the idea that I look at all my samples and they were sampled independently of each other. So you know how you and I were out there asking customers, are you a first-time buyer? Well, if we would have asked the same person somewhere in there, we would have dependent samples. They wouldn't be independent anymore because we both shared a person. And that would mean that we wouldn't be able to use the sampling distribution for our example. Darn, that happens. We want to avoid that. That's just one instance of failing at independence. The other thing is, and I've said this before, it must be large enough. I'm going to do that, just pause. And must be large. What do you mean? Well, let me get specific, just it'll be okay. The one thing I want to warn you about as you do this is one of the #1 complaints I get from employers who have students who work for them and engage in doing statistics is that a lot of students will just willy-nilly do some things like, oh, I'm going to assume this is normal and just go crazy without checking their assumptions. Don't be that guy, because, you know, you should think about whether or not you should before you think about whether or not you can. Just like robbing a bank. You probably shouldn't, so don't think about how. I don't like that analogy. Think about Jurassic Park. Just because you can make the dinosaurs doesn't mean you should. That one's better. All right. We also need randomization. One of the things you learn in Chapter 8 is that if you don't have a random sample, then your sample is likely to have biased sources in it and or be over or underrepresenting certain groups. And if that happens, then your data, your sample, doesn't do a good job of representing the population. You want your sample to look like the population. That way, when you're making your calculations, your results look like the population. So make it random, yo. Here's what I'm talking about when I said sample size. We have first what's called the 10% condition. This is just the requirement that if you are going to be sampling, you can't have your sample be an oversample, as in it accounts for more than 10% of the population. If you do this, it is most likely that you have one group that is overrepresented, and that's the main reason why we don't want this. The next condition, and this is the one that's probably the most important, is what's called the success-failure condition. So if the probability that something happens is like 2 out of 10, and you do a sample of 10 people, then how many successes should you have? You're like 2/10 times 10, that's 2. And you've also counted the number of successes. That's why this calculation is, the sample size times the probability of success. That's called your number of successes. And then your failures, or number of failures, is your n times your q. In case you forgot, q is the probability of failure, or the opposite, or not success, 1 minus p. And we need both of these to be at least 10. So when I say both, I mean both. You can't have one be 10 and one be 8. They both have to be at least 10 in order for you to use the normal distribution, or the normal sampling distribution. Now, you might be wondering why at least 10? Well, if you do anything smaller than 10, then you probably end up with something that has a slight skew to it, either to the left or to the right, depending on if it's your failures or your successes that's skewed. Or sorry, that's more than 10 or less than 10. So, in order for it to be large enough for it to be detectable and look normal, they both need to be at least 10. This is the easiest one to check, but you know, it's good. Let's do an example. 95. There we go. That took me forever, and I'm not going to be able to delete that. So 95 is a p hat. It's a sample value out of 160 that we're interested in, not out of the true proportion. Okay. So, is it independent? I'm pretty sure they don't get their seeds from all one source. So, and one seed germinating, sorry, I just did the all one source. That's actually the randomization idea. So it's probably they get them from a bunch of different people and throw them all together in a big pot and throw them into packages. So it's probably random in that sense. As far as independence goes, germination is probably independent. Just because one seed pops up doesn't mean the other one's going to. So one of them growing, germinating, isn't the same as all of them growing. Or, you know, just because the guy grows next to you doesn't mean your conditions are good, and so you might not grow too. All right. 10%. One packet is probably less than 10% of all their seeds that they manufacture, because if they only made one packet, it was 10%. That means they made less than 10 or exactly 10 packets, and they're probably out of business then if that's the case. Anyway, here's the success-failure condition. So in order to do the success-failure condition, I take my sample size, which is 160, times my probability of success, which is 92%. That's the rate at which my stuff germinates. I multiply those two together, and I come up with 147.2, which is bigger than 10, so we're good. And then I'm going to check my failure. I usually check the smaller percentage first, but this time I didn't for some reason, because if it's going to fail, it's going to fail for the small one. So we're going to take our number of seeds, 160, times our rate of non-germination or failure rate, which is 8%. Multiply those two together and you get 12.8, which is just bigger than 10. Perfect. We're good to go on those. Now let's do some calculating. I'm hoping you notice that we need to come up with the normal distribution for this sampling distribution in order to be able to calculate any probabilities. So the first thing we're going to notice is that, oh my gosh, there's my mean. There's the mean of the normal distribution. It's the germination rate, and then I got to use the germination rate right here along with the failure rate and the standard deviation in the square root to come up with the spread. Now, I rounded this. I'm going to warn you right now that when you're doing this, since it's proportions, it is quite possible that your spreads are going to be very, very, very tiny. Round more than you think you would. So go out a couple more decimal places. If you're one of those people who's really tempted to stop at like 1 or 2, do like 3 or 4, because you super should take more than what you normally would have. I rounded like the devil and just did 3. Okay, so I'm going to find the z-score. I'm doing this by hand. If you've watched any of the videos or intend to, you'll notice that I'm going to do all of those with technology. So typically what you do is now I'm going to do a normal calculation. So I'm going to take my score, which is that 95%, subtract the mean of the distribution, which is 92, and then divide by my standard deviation, which I just calculated to be 0.021. I'm going to put that all into fraction, calculate my z-score, use the z-score to find my probability. So the probability, my pen is just not working at all. That's great. The probability I was interested in was that my sample proportion, aka my germination rate, was greater than or equal to 95%. That's so legible, it's not even funny. Equals my p. Wee-hee-hee. Okay. So as you look at this, I'm hoping you notice that what you would do next is you'd pull out your standard normal distribution. Note that the standard normal distribution only gives you areas to the left. Look up the z-score. That would give you the left area. Subtract that from 1, and that would give you the value that I came up with, this right value. Yay! If you forgot how to do that, you need to go to Module 0 and the Chapter 7 review. Ta-da! How about another example? In April of 2013, a Gallup poll found that 1,495 out of 3,559 respondents thought the economic conditions were getting better, with a sample proportion of about 42%. We'd like to use this sample proportion to say something about what the population proportion, P, aka of the entire population, think about the economic conditions and whether or not they're getting better. So I want to take this sample and say something about what does the population really look like? Let's see how we do that. So I'm going to take a statistic and use it to estimate a parameter. So remember, we're using spread to find the true population proportion. One of the key things about this is the fact that, well, I don't really know P. Originally, we would use this formula to find the spread of my normal distribution. But unfortunately, I don't know P. I only know P hat, so I'm going to be stuck using that, which is unfortunate. So I'm definitely using the standard error here, which, as you remember, is a standard deviation, but I'm using P hat, I'm using the sample stuff instead of the population stuff. So I have introduced some estimating here, but if you have a good sample and it's large enough, in this case we meet those conditions, then I really am not violating anything. The central limit theorem says that the standard error will approximate the standard deviation well enough to use it as the spread. So I'm going to use it. So using the fact that this is normal, we should expect that about 95% of all samples of size 3,555, but U.S. adults would have a sample proportion within 2 standard errors of our sample proportion P, our population proportion P. So that is, we're 95% sure that P hat is within 2 standard deviations of P. How are we going to do this? Well, we're going to just calculate that. So I'm going to take P hat, which is 42%, and add 2 standard deviations into it. So 42% plus 2 times 8%, 2 standard deviations. That's 1.6%, so I'm going to add and subtract that and get a range from 40.4% to 43.6%. This is going to be our estimate. So our confidence interval, in case you haven't noticed, the title changed to confidence interval somewhere in here. So the 95% of these scores are going to be between these two. This is a little bit of a strange idea, but we are going to be 95% confident that the true proportion of U.S. adults who think the economy is proven is given by somewhere between 40.4% and 43.6%. Let me be more specific about this description because this slide is just way too short to describe what's really going on here. So I'm going to talk to you first about what you can't use this to say and about what you can. So here's what we'd hopefully be able to say. Hey, it's 42%. Hold your horses there, buddy. Okay, we'd all like to think that the sample proportion is the population proportion, if you've done a good enough job sampling. But in all likelihood, it's probably not. There's no way to be sure that the proportion from the sample is the same as the population. It's just not even possible. It could be, but you'd have to get like fantastic magic sample. It's probably not true. Okay, it is probably 42% of adults that think the economy is improving. And again, we can't really be certain that it is exactly that value. So be careful. It feels like I'm saying the same thing in these two, but be careful. The first one I'm asserting that the sample is the truth, and this one I'm saying that it's probably true, that it's exactly that. That just seems a little bit more specific than necessary. One thing you want to keep in mind with statistics is that hopefully this class teaches you a healthy dose of skepticism. Anybody who tries to use statistics to say assertively something is some value or to make some claim that's definite, you should be suspicious. Because really statistics is about gathering data and making inferences, which means gathering information and saying, where does this evidence take me? What can I, think is going to happen? What do I predict? And again, you're doing a prediction. It's not always going to be the truth. You're trying to predict. All right. We don't know the exact population proportion of those of U.S. adults who think the economy is improving. We do know it's between 40.4 and 43.6%. Here's the thing. You don't know whether or not that's the actual interval. You don't know if you've managed to cover everything. You've only grabbed 95% of all possibilities because you went 2 standard deviations in each direction. That means I'm not so for sure that this is exactly where it lies. Okay. 4 is just kind of like another variation on 3. Ready? We don't know the exact proportion of U.S. adults who thought the economy was improving, but the interval from 40.4% to 43.6% probably contains the true proportion. This is close to correct. But what do you mean by probably? We can actually do better than that. We just did probability. I mean, come on now. We know how much this is. So what does that 95% confident thing really mean? What does it mean that we say that our confidence interval contains a new proportion 95% of the time? Well, we're 95% confidence, which means, about 5% of the time, I'm going to fail. I'm going to miss the true value. Oh no! We know that since we have variation from sample to sample, if we happen to have gathered a not so representative sample completely by random chance, about 5% of the time we will miss the true proportion. Let me give you a visual that kind of helps you with that. So as you look at these dots along this graph, they each represent a sample that was gathered, and then these bands represent adding 2 standard deviations, and then to get the upper part, and then subtracting 2 standard deviations to get the lower part. As you look at this, each of these hopefully capture the true proportion, which is that green bar through the middle. And most of them do, except for one, this guy. Oh no, he's above the green line. He failed to capture the true proportion. This happened 1 out of 20 times. P.S. That's like 5%. So it's quite possible that even though you have a good confidence interval and you really intended well in what you were up to, you're not going to capture the true proportion all the time. It happens. You may be missed. So, although we'll never be sure our confidence interval really contains the true proportion, the normal model assures us that about 95% of the theoretical possible intervals are winners. So about 95% of the time you got this. So the true proportion is somewhere in there. That's why you have a range of values. This is why we're 95% confident that our interval is the winner. And we want to make sure we emphasize that in our interpretation and not miss it. Because you got to be careful. You don't want to say more than you actually can. All right. So what assumptions do we need? Independence assumption, we should check that we have randomization. We need 10% so that we don't oversample, and then we can safely proceed. We want to check the success and failure condition, and we want to make sure we have at least 10 successes and 10 failures, and that's what that means in order to be able to use this. All right. Let's talk about one of the more important components of the confidence interval because it can help us in doing some of our calculations, and in particular help us figure out what size sample do I need. I'm interested in what's called the margin of error. So our confidence interval that we've done previously was our sample estimate, p hat, plus or minus 2 standard errors. So remember it's, looking at an estimate plus or minus a z-score times a spread. And that's what is the margin of error. So when you're creating your confidence interval, you're essentially doing this. You figure out where your value is, your p hat, and then you add the margin of error to arrive at p hat plus the margin of error. And then you subtract your margin of error from your p hat to get the other bound. So as you look at this, p hat is always in your interval. It's at the center. Really what this is telling us is it's the extent or the width of one side of the interval. There's a little bit of a catch-22 to this. The more confident we want to be, the larger the margin of error must be. Why on earth is that true? Well, we can't be really 100% confident that the proportion is between 0 and 100%. So we really would want to be very confident the interval goes from like 41.9% to 42%. But every confidence interval is balanced between certainty and precision. Fortunately, we can make both sufficiently certain and sufficiently precise to make these statements true. So what? If this seemed like nonsense, just wait, there's the next slide. Ha! So your choice of confidence level is usually somewhat arbitrary. We usually choose between 95, 99, and 99% because these are the common ones. Now I have seen some crazy ones. I even saw a biology paper once where they decided to use 82%. I'm not really sure where that came from other than who knows. But we generally think of confidence level as something based on a central area. So I'm going to draw this in. We would think about the yellow zone. As our confidence level. I'm just going to abbreviate that CL because I'm worried it's not going to fit. Okay. So as you look at the confidence level, it's going to contribute to your margin of error by the following. Margin of error is some z-score, how many standard deviations you want to move away from the mean. So we'll be thinking how many standard deviations times how wide the standard deviations are. So how far am I moving? And those are based on your confidence level. So you get two of these, z star, the negative twin because this has reflectional symmetry. Now, one of the things you know is that to be more confident, to have more area in this yellow middle, I need to, have more area. So in order to do that, I'm going to have to move my z-stars further away. So that would give me more confidence. But that means that this value is larger, which means my margin of error is bigger, and that means the spread of my interval is larger as well. Crap, that's not good. I don't want my interval to be really far out because that gives me more values that it could possibly be. So what you'll want to do instead is you're like, oh, I got to move the confidence level in, but then I'm less confident that I got the truth. My area is smaller and my confidence level is smaller, so I might be like 80% sure, maybe 75% sure, but my margin of error, is smaller also. That means I've got fewer values. Maybe it's only like, 1% wide. So I've increased my precision. I'm more likely to I've got less values that could be the true proportion, but I've increased my spread, and so my interval is less likely to have it because I've got a lower confidence level. And as you look at these are the most common ones. If you're worried about memorizing these, don't. One of the things I give you for your tests are formula sheets, and these are definitely on there. You're going to use them a bunch. I've used them so much that I have them memorized, which I'm mildly ashamed of. Okay, so let's talk critical values. Here's the one for 90%, pictured with the 1.645 and the negative 1.645. If you're ever confused as to which one you should use for your confidence interval, either the positive one or the negative one, it does not matter because you are adding and subtracting. You're doing both. So if you were using the positive one, you do the positive one, you end up adding it. You do the negative one, you end up subtracting it. If you accidentally use the negative z-star, you'd end up adding a negative, which is subtracting. There's the negative one. And then you'd end up subtracting a negative, which is adding, so you just did both of those again. Didn't matter. Ta-da! All right. So the one proportion z interval is found from taking the estimate, p hat, adding, subtracting your margin of error, which is your z-score, times your standard error, where your standard error is found by doing your success times failure divided by n and then taking the square root. Let's do an example. So in March 13th, I wish I could fix this. Oh, in March of 2013, workers at a greeting card company called Edit 66 took their boss's hostage. The company chiefs informed the employees that were going to be laid off that they would not be receiving their severance pay that they were legally entitled to. These incidents have been nicknamed the boss nappings, and they're actually not uncommon in France. When I first read this, I thought it was like boss nappings, like they're going to go take a nap, which was horrible on my part. And then I realized it was people being kidnapped. So not a great thing. Anyway, so what did the other French adults think of this practice? Were they sympathetic? Did they approve? Were they understanding? Let's find out. So Paris Match found that 63% of French were supportive of such an action using a poll. This poll was based on a randomly selected representative sample of 1,010 adults. What can we conclude about the proportion of all French adults, who sympathize with the practice of boss napping? Not the boss napping, but kidnapping the boss. Anyway, the first thing we should do is check our conditions. Is it random? Yep, they told us so. Is it 10? Is it less than 10%? Yes, because that would be like saying there are 10,000 people in France. I am currently in Midland, which has way more than 10,000 people and is way smaller than the entire country of France. Just so you know. So it's probably not more than 10%. Check. Let's check our failure and success. So we do our sample size times our probability of success, which was at 63%. And we come up with 636. That's bigger than 10 by a lot. Usually when you have a really large sample, it doesn't matter so much unless one of these is super tiny. Now we got to do our failure check. So again, n sample size times failure probability. 374 is super bigger than 10. We are good to go. We can create a confidence interval using Z. All right. So the first thing I'm going to do is I'm going to create my standard error. We're going to need this to build our confidence interval. So we got to do the square root of success failure divided by sample size. Take the root. I'm rounding this to 0.015. I'm going to take that and multiply it by my standard normal. So my critical value for here I'm going to use is 1.96 because that's the one that's associated with 95%. Do not use the 68, 95, 99.7 rule for these because you will be rounding too much, especially since proportions can get so tiny. All right, so we're going to calculate our margin of error. Woohoo! It's 0.029. So I'm going to be adding and subtracting my margin of error, which is the same as the interval, 6.601 to 0.659. Let's write a good interpretation of that. So what does this actually mean? The polling agency Paris Match surveyed 1,010 French adults and asked whether or not they improved or were sympathetic or disapproved to recent boss napping actions. Although we can't know the true proportion of French adults who were sympathetic, really without supporting outright, based on the survey, we can conclude that we are 95% confident that between 60.1% and 65.9% of French adults were. It's kind of high. It's more than the majority, so it's like, hey, you shouldn't promise things you can't deliver on. Bossy, bossy boo. I'm not advocating kidnapping your boss. Covering my own ass on this one. Don't kidnap your boss. All right, so what do we want to do if we want to get a narrower confidence interval? We want to focus on actually choosing sample size. I'm hoping one of the things you notice is that messing with confidence level, it does change your interval's width and everything, but it doesn't really help you all that much. So what we want to do instead is look at the margin of error and ask, how can I reduce my error? How can I make these intervals narrower so that they're more accurate without changing my level of confidence? So you look at this and you're like, I can't touch Z because that's my confidence level. I can't touch P or Q because I can't change my sample. That's cheating. What I can change is my sample size. I can mess with N. So let's suppose our company wanted to offer a new service and wants to estimate it within 3%. The proportion of customers who are likely to purchase this new service with a 95% confidence, how large do they want to sample do they need to be able to do this? So what we're going to do is we're going to plug in what we know. We want to be within 3%. We're 95% confident. The z-score associated with that is 1.96. There's our 3%. We're going to set that equal to our PQ over N. So I don't know P and Q. Poop. I don't know N. There's too many unknowns. What the heck am I going to do? Well, I mean, if you know P, then you know what Q is because it's 1 minus it. Oh, dude, what do I do? Well, I use 50%. It's actually the worst case scenario. If you'd like to see exactly why it's the worst case scenario, it involves solving quadratic equations. I don't know how interested in algebra you are or how much you remember from your algebra. you can go ahead and look at how to do that. There's a couple videos on how. All right, so what we're now going to do is we're going to compute n. So you set up your equation, put in our p, put in our q. Remember, q and p, 50% each. You'll solve that for n, and you'll get 1,067.1 peoples. You can't have 0.1 of a people. So what you're going to do is you're going to need at least 10,068 people, because that will keep it as small as at least 3%. So by rounding this up, since the n is in the denominator, I'm making sure that I'm at 3% or something less. Rounding up will make sure that you divide by something larger, and therefore your value overall will be smaller than 3%, with a confidence level of 95%. If you've ever looked at any type of polling, usually this is a pretty acceptable level. What's a normal acceptable level for a margin of error? Usually we go about 5% or less, you know. However, to cut your margin of error in half, you actually have to quadruple sample size. You're going to see some more of that when we hit chapter 11. And sometimes the cost of doing this to increase your sample to the point where you actually have less error is proclivative to actually doing it. So if you're looking at this and like, oh, what's it going to cost to survey like 100 people versus 400 people? That's kind of scary. You might go with something sort of sensibly in the middle, like 200 or 250 instead, to save yourself some money and accept that your margin of error is going to be larger than 5%. All right, that's all. Let's go through a quick summary. What can go wrong? No, seriously, what can go wrong? Be careful. Sampling distribution is about a sample, not an individual. Don't confuse it with the distribution of the sample. Beware of observations that aren't independent. If they're not independent, you can't be doing this. Watch out for samples that are too small. You'll probably notice they're too small when you do the success-failure condition, but keep in mind if it's small, it's probably not normal. All right. Be sure to use the right language when you're describing your confidence intervals. Don't be talking about the sample. Remember, this is about the population. We're trying to estimate the parameter. We know what the sample looks like. We already have that answer. It's not useful to... Yeah. Don't suggest that parameters vary. They don't. They're fixed. Don't claim that other samples will agree with yours, because they probably won't. Don't be certain about the parameter, because usually there's no way for you to actually know what it is. Don't forget, it's about the parameter. Ooh, I'm sort of beating the dead horse on this one. Don't claim to know too much. Again, anybody who claims to know too much probably doesn't know enough statistics to be doing this. And don't take responsibility. What do I mean by that? Sounds horrible. This is like giving out life advice. Don't claim to know too much. Don't take responsibility. I mean that you shouldn't be talking in the first person when you do this. It should be in the third person, because we're doing formal writing. So I keep saying we when it's just one of us doing this. You doing your homework and me helping. I guess that is kind of a we. The colloquial we. You should be saying we. We! Okay. Watch out for violations of the assumptions. If you violate any of it, you shouldn't be doing normal. You can't be doing a confidence interval. There are other ways to handle this. There is other statistics out there that will handle these situations. We're not doing those. All right, what have we learned? Woohoo! We know that variation exists from sample to sample within the sampling distribution, but as long as you sample well, as in random, and large enough, as in, make sure my conditions are met, then we get something normal. So be thinking, gotta sample good, gotta sample large. We're good. All right, and then the meaning behind this is that I want to be able to use the sampling distribution to estimate the population proportion, which is the mean of the distribution. Be careful when you're interpreting the standard deviation of the sampling distribution. The standard deviation is really the most important information about it. I said that in here, I typed it too, it's fun. The sampling distribution, really, when we look at its spread, it's very intimately detailing how it gets spread out depending on what size your sample is. Woohoo! Be careful when constructing a confidence interval and making sure that you're using P or P hat appropriately. If you know P, then you should be using it. More often you won't though, so you'll be using P hat, and that's okay. Be careful with your critical values. Don't use the ones from the 68, 95, 99.7 rule, because those are rounded and could possibly cause you to be off by quite a bit because they are rounded. So make sure you use the values in the table I gave you and that you'll find on your formula sheet. Make sure you interpret the correct interval correctly. Oof. It's very specific what you're saying. You want to make sure you mention confidence. You want to have some context, and you want to actually tell what the interval is. You don't want to pull the wool over anyone's eyes and say anything crazy in it either. Make sure you're talking about the parameter, not the sample. not the statistic. Make sure that you pay attention to sample size. Margin of error is the best way to encourage yourself to have precision in your measurements, as in, I'm not too far off. If you don't understand the difference between precision and accuracy, Google it. There's some lovely pictures about darts that help. If not, ask me. I'll show you. Sample size is super important here. Last but not leastly, always check your conditions, or check yourself before you wreck yourself, because that's how we should roll. Make sure you're able to invert the margin of error calculation. If you can't, I have 3 videos on how to do that. Watch them. They will help you. Peace out, Girl Scout.